Hi, we are Project Unagi, and we are a team of 5 based in London, and we want to deliver a more sustainable battery future. My name is Oskar, and I'll be talking to you about why we need potassium-ion batteries, or KIBs. Before I talk to you about the need for KIBs, I first want to talk about lithium-ion batteries, or LIBs. The annual demand for LIBs is rising exponentially, with the demand for LIBs being 500 tons in 2003, whereas in 2020 it was 6,500 tons, and it's rising at a more rapid rate than ever. But even though the demand is increasing, the abundance of both lithium and cobalt, the two main materials in LIBs, are decreasing, and eventually the cost of LIBs will stop decreasing and will at some point begin to increase. As well as this, less than 1% of all LIBs are recycled, and because of this, there is a projected shortage of batteries between 2021 and 2023. This is not sustainable, however, because in the growing market of electric cars, LIBs hold 95 to 99% of the market for the batteries inside of these cars. And since the UK is banning the production of petrol-based cars in 2030, the demand for LIBs will increase further, hence the need for a new abundant battery. In comes the KIB, a new battery technology which is less impactful on the environment, achieves similar and better stats than LIBs, and comes in at a lower cost and therefore will be more attractive to companies, so therefore can be a suitable replacement for LIBs.
We've selected M13 bacteriophage as the structural component of our battery on account of its interesting biological properties. M13 bacteriophage, aka Escherichia virus M13, is a filamentous virus in the Enovirus family, which reproduces in gram-negative bacteria, for example E. coli, and is harmless to humans. In terms of structure, it's a linear virus consisting of a protein coat and a circular chain of single-stranded DNA, which is 6,407 bases long. It's commonly used in genetic engineering, as the simple genome and prominent and accessible surface proteins provide a versatile and highly tunable vehicle for peptide expression. To ensure our virus binds to our Prussian blue analog cathode, we'll use site-directed mutagenesis to fuse tetraglutamate groups to the terminus of the G8 proteins, which is the major coat protein, of which there exist 2,800 copies. The resultant virus is a tetraglutamate M13 virus, also known as E4 virus. The additional carboxyl groups in E4 virus result in an increased level of ionic interaction with cations, thus guaranteeing a binding affinity with our cathode. Subsequently, to induce binding affinity with our carbon nanotubules, we will fuse our Solinus peptides to the N or outer terminus of G3. This peptide group is able to bind to CNTs via a process known as pi stacking interaction. These viruses have many advantages for nanotemplating efficient batteries, as they are simple and time efficient to manufacture. The protocol for producing a large number of our viruses is simple, requiring them to be introduced to an E. coli culture, then precipitated by the addition of polyethylene glycol. Due to these self-replicating properties, a manufacturer can produce as many viruses as are needed from just one specimen. As such, our modified M13 virus represents a viable and inexpensive mechanism of bio-nanotemplating.
The ubiquitous lithium-ion battery's component metal, lithium, is falling quickly out of supply. A promising novel battery technology, using the much more abundant potassium-ion, paves the way to higher energy density and ultimately the future of batteries. Our battery uses the potassium-ion, exchanged between a graphite anode, chosen for its favourable intercalation with the ions, and a Prussian blue analogue. The analogue, namely potassium manganese hexacyanoferrate, will provide the potassium ions and has greatly beneficial electrochemical properties, maintaining high stability during ion transfer and providing conductive ion channels thanks to the nanoporous crystal structure. Our hexacyanoferrate cathode crystal is partially hydrated, further boosting the electrochemical performance and making use of the voids in the crystal phase. The potassium bis-fluorosulfonylimide aqueous electrolyte is used to maintain and protect the solid electrode interface at the cathode and improve the rate of ion transfer while sustaining a well-suited environment for our bacteriophages. The modified viruses will bind to carbon nanotubes in suspension, which are an incredible conductor material, and attach to the hexacyanoferrate cathode. This will assemble a network of highly conductive ion channels, increasing the conductivity of the cathode and enhancing the performance of the battery overall.
As mentioned, lithium-ion batteries have their fair share of problems. For example, the scarcity and pollutant effect of many of the requisite materials, namely lithium and cobalt. This is the problem we seek to solve by developing efficient potassium-ion batteries. Unfortunately, the exhibited electrochemical properties of current potassium-ion batteries, or KIBs, are insufficient to meet the requirements for widespread use. As such, our decision to utilise viruses to create a more efficient network for ion transfer and provide a greater conductive surface has helped us to produce a protocol for the manufacture of batteries which exhibit not only the intrinsically superior qualities associated with using potassium ions, lower cost, lower scarcity, cheaper manufacturing processes, and less pollutant-affecting disposal, but also electrochemical properties which are similar or superior to those of widespread lithium-ion rivals. To achieve this goal, we have selected the PowerStream LIR 2032 as our target. It is a rechargeable lithium-ion coin cell which exhibits an energy density of around 90 watt-hours per kilogram. It's a common choice for watch batteries and remote-controlled toys, and sells tens of thousands of units per year. As such, if our prototype can improve upon the cycling characteristics and power density of this battery, we can demonstrate the commercial potential of potassium as a cathode material. The research upon which we've based our work demonstrates that with a similar system of virally templated carbon nanotubules, an increase of 68% in specific capacity and an energy density 3 times as high at specific power of 4 kilowatts per kilograms can be attained. As such, we are confident that even with the scope of our project, we can achieve similarly elevated electrochemical performance, allowing us to outcompete other rechargeable battery options in the market. You may now be wondering, the concept and technical background sound great, but how do we make these batteries and will people want to buy them? Let me answer that for you. The battery market now for coin cell batteries is currently valued at $3.89 billion and has a year-on-year growth of 0.45%. Of this market, over half of the demand lies with retail consumers, which allows us to sell to them directly. As discussed in the technical portion of our presentation, our batteries are rechargeable, projected to be more efficient and cheaper than our alternatives, which allows us greater pricing leeway as our batteries offer greater long-run saving to our consumers. Our material and manufacturing costs for this product currently reach well below the 90p per battery threshold, primarily due to their 86% reduction in material costs from lithium to potassium. Given the complexity of our product, the manufacturing processes are surprisingly simple, using tried and tested battery and gene editing techniques. Whilst the manufacturing process is long, all it requires is easy accessible materials and machinery which are already common to the battery industry, nothing more. To summarise, we are using the principles of synthetic biology to produce a battery which is inexpensive and more sustainable than its lithium-ion battery counterparts, while also exhibiting similar or better electrochemical properties. Work is currently underway on a prototype, and we are excited to see what the future holds. Thank you for your time.